Welcome. This is the presentation of the Town of Acton and Acton-Boxborough Regional School District Electrification Roadmap. The Town of Acton and the Acton-Boxborough Regional School District collaborated on this analysis. Next, Ian, please. This was funded with a really generous grant from the Massachusetts Municipal Vulnerability Preparedness Program. We received $70,000. And this enabled us to work with engineers at Salis O'Brien, who are here today. And they put together a robust analysis of the capital, operational, and conversion costs for electrifying our municipal and school buildings. This is really in line with the Town of Acton's climate emergency declaration that was passed at the special town meeting in 2020. It calls for net zero as quickly as possible, net zero emissions as quickly as possible, with a target date of 2030. And it aligns with the Town of Acton Climate Action Plan, which was also recently published and can be found on the Town of Acton website under the sustainability page. And key to meeting that net zero emissions goal is electrifying our buildings. Buildings make up almost half of greenhouse gas emissions here in Acton. And if we're expecting residential properties, commercial properties, industrial properties to electrify, it's really important for the town to lead by example. And so the good news is we already count on one fully electric building, the fire station, which is a net zero building. It is fully electric with ground source heat pumps. Some of the energy comes from solar, and then the rest comes from renewable energy credits that are purchased by the town through the Acton Power Choice Green program, which supports renewable energy projects in the Northeast. And with that, I'll hand it over to Kate Crosby, the Energy Manager for the Acton-Boxborough Regional School District.
Good morning, everybody. We were thrilled to partner with Town of Acton on applying for this grant and then on pursuing the project with Salis O'Brien and doing this electrification roadmap analysis that you'll be hearing about from them. There's been some additional context for electrification with work going on at the district. We are shortly opening a brand new building, a brand new school building that is an all-electric geothermal net zero school building. It was constructed for essentially the same cost as a conventional gas-fired building, and that's very exciting. It's pretty straightforward with new construction now to make buildings all electric without additional cost and operate them without any on-site emissions. So that's a tremendous advance. I want to mention that the Town of Acton has opened a all-electric geothermal fire station recently. So we have two public buildings in town that will be operating without on-site emissions. And in addition, the district received grant funding to take a look at 11 rooftop units at the high school that are aging out and what would be involved in electrifying them. And the analysis showed that the district will actually save money by electrifying them rather than by replacing them with gas-fired units. So every situation is different, whether it's your home or a public building or a commercial building, and needs to be analyzed. And that's why we need engineers with skills like the folks who you're about to hear from, is to take a look and do those analyses. I want to, the collaboration between the town and the district has been great. And one of the things that you'll hear about is that there are two different timelines for the two different organizations that are cooked into this report. The Town of Acton timeline is pegged to 2030 in keeping with the town meeting resolution and the climate action plan development. And the school district timeline in this report is pegged to 2050. The district has not yet taken up the conversation about how to best approach electrification due to some other challenges with COVID and other things going on. So we will be discussing that, but in this report, the analysis is pegged to the state goal of 2050 for net zero greenhouse gas emissions. The building sizes are different. The school buildings are much larger than the town buildings, and some other variations that you'll hear as we go through the report today. I want to mention that the analysis for the district is focused on buildings on the campus. Because we were hoping for some synchronicity with the campus setting, and they are all on a single account with Eversource. There are a couple other buildings that are not included, and certainly the lessons from this we will be applying across our entire building portfolio. And with that, I'm going to hand this off to Salis O'Brien. Good morning and welcome.
Good morning. What we have on the screen here, I guess, is just some of the electrification roadmap goals that we were tasked with exploring as part of this, as part of our study. Some of the highlights of that we wanted to look at: first, removing fossil fuel-based systems and replacing those with electrified systems such as heat pumps, air source, ground source, VRF systems. We also wanted to look at the feasibility of additional PV, solar thermal, battery storage, and other ways to implement renewable technologies into the buildings. Next slide, Ian. Just a little bit of an introduction to ourselves first. My name is Mike Hovanek, the Senior Mechanical Engineer and Project Manager for this project with Salis O'Brien. Also on the call today is Ian Davies and Jake Shepard, both also mechanical engineers. The three of us kind of represented the core team from Salis O'Brien, but we also had input and participation from our electrical engineers, our geothermal consultants within our firm, and other industry experts that are focused on electrification across the U.S. So just here today, we just have the three of us, but we had a much wider group participating in the overall project. And Salis O'Brien has been, we're industry experts in electrification. We've been working on providing solutions to campuses, to our clients across the United States that are focused on reducing greenhouse gas emissions, reducing use of fossil fuels, whether it's fuel oil or natural gas, or also just looking to improve the energy efficiency of their existing systems. And so we've done that largely with universities that have college universities with campus settings, but we've also worked with large corporations such as Epic, Ford, that also have a large campus that's often well suited towards electrification. But more increasingly, we're getting involved in working with municipalities like Acton and like the school district that are also focused on trying to understand how they can electrify their building systems. So one of the key things we'll be talking about during this today, and what you'll see in the actual electrification roadmap, is we often talk about building conversion, or we talk about low temperature hot water conversion. And it's really one of the things that's kind of at the crux of this entire electrification process. In buildings that traditionally use either steam or high temperature hot water, we have to go through, as part of the conversion process, we have to convert that to a heating medium that is easily generated through electrical sources like heat pumps, heat pumps or heat recovery chillers. And what that really entails, what does it mean to convert the building? What we're really talking about is going through and taking out items like steam radiators, old cast iron steam radiators, and replacing them with more modern low temperature hot water radiators. And what we're looking at here on the screen is we got a before and after picture of one of our projects. This is out at Carleton College, which is in Minnesota. It's a very, very cold climate. And we went through and replaced the steam radiator on one side with a modern low temperature, modern metal panel radiator. It's at the heart of what we're doing. That's kind of the basics of it. But why it's important is that it enables us to start using technologies that can generate heating hot water temperatures suitable for generation by electrical means like heat pumps.
And so, like Mike was talking about, we are coming up with these electrified solutions for buildings, and there are a lot of different technologies out there that can generate this low temperature hot water and also chilled water for cooling with electrical energy input. But in order to figure out what the best technology is going to end up being, we first need to start by creating a baseline case, or we call it as a business as usual model. And so what this is just a energy model of the buildings as they currently stand. And so we take a variety of inputs of the current situation, including regional weather data, energy usage data from utility bills. We also go through all of the existing buildings. We do an inventory on all the systems, what their existing efficiencies are, and we put that into our model, and we can, from those inputs, get a few outputs, which are thermal profiles, which we'll show you in a minute. And then also we can get end use energy by different utilities. So the natural gas and the electrical consumption for each building, the corresponding carbon emissions, and then the cost associated with using that thermal energy. And so in order to make sure that our model is working correctly, we calibrate it. And we do this by taking the actual metered information in the blue here and comparing it to what the model is calculating. And we do this for each of our buildings, and we make sure that we kind of adjust some inputs and some settings in our model to make sure that the annual heating and cooling energy is within 1% of each other. So the calculated is 1% accurate from that sense. So we do this for all the buildings for heating and cooling. So here's we were just looking at the cooling energy, and this is the heating. You can kind of see that everything's relatively similar. And using the energy model, we create this thermal profile. And we'll be showing you a lot of these today, but I wanted to kind of give you the basics of what these are. So in the red, we have the annual heating load. And on the y-axis, you can see this is in monthly, average monthly MBTU per hour. So that's basically the average monthly energy usage in heating in red. And so you can see that it peaks in January, and then over the summer months, it's basically zero. So, and then on below the zero line is the cooling load. And you can see that in August, we have a peak, and over the winter, it's very close to zero. So this is all for the public safety facility. And this is a really important graphic to use because it's how we're going to apply our electrification technologies, kind of overlay them onto this graphic to figure out what options are best, and how we can kind of take all of this red, which is heating and typically natural gas, and convert it to electric. And from that thermal profile, we have a few different outputs. We're able to look at the annual electric heating, these kind of the utility usage, the energy usage, the utility costs, and also the corresponding greenhouse gas emissions down here on the bottom. And that's the units that we use for that are metric tons of carbon equivalent per year. And that's just a unit that we'll be kind of showing you a few different times here. So I want to introduce that now. So what this does is it establishes a baseline for moving forward, and also by having these three different metrics to look at, we can focus in on one of them. And so for our project, the goal here was to reduce the carbon emissions with the electrified system. So we really focused in on these numbers and getting these down as far as possible to close to zero. So for that same public safety facility, here's the thermal profile, but now we've added in our electrified systems. And so what we do for each of the buildings is we evaluate different scenarios, different electrified systems, and we focus in on a couple of key parameters like the system efficiencies, the capital costs of the systems, the operational costs, and then also the constructability of the system. And so for the public safety facility, we landed on an all air source heat pump system. And so these air source heat pumps are going to be located out on grade outside, and they would provide hot water and chilled water for 100% of the building's heating and cooling load. And here are kind of the results of inputting those systems. And so here we can kind of see that the overall energy usage goes down, the overall energy cost goes up a little bit, and the overall carbon emissions goes down quite significantly. And it's not zero in this point, and we'll talk about this a little bit later on and show you why. This is still a kind of a positive number here, but it's because we're looking at the reference year 2030, and that'll come into play in a little bit. And so we also we found electrified systems for each of the town buildings. So here's the town hall's electrified system. It's pretty similar to the public safety facility where we have 100% air source heat pump system, heating and cooling. And here's the Acton Memorial Library's system. It's air source heat pump, heating and cooling, but we also have a supplemental electric boiler up here in red. And this takes care of all of the coldest days of the year, the peak heating days when it's down, around 0 degrees. And what we did for the conversion years is we created these timelines, and we ultimately use these in our kind of economic analysis. But what we did to determine the years, the suggested years for building conversions for the town buildings was really driven by the 2030 Acton Climate Emergency Declaration goal. But we also factored in maximizing the existing equipment's lifespan and timing up conversions with planned renovations in these buildings. And so here is kind of the cumulative greenhouse gas emissions for the town buildings plotted out over time. And so what we have here in the blue dashed line on top is the business as usual greenhouse gas emissions. And then in the red is the town buildings under the electrified option, the natural gas greenhouse gas emissions. And then in green is the town buildings electrical greenhouse gas emissions. And so one concept that we want to introduce here is the fact that this line slopes down, and this is associated with the greening of the grid in the state of Massachusetts. So the state of Massachusetts has committed to reducing greenhouse gas emissions associated with the electrical grid to 0 by 2050. And that's why down here the greenhouse gas emissions are in fact all the way 0. But also it's why we still have over in 2030 some greenhouse gas emissions, because even though we've converted all 3 of the town buildings and our natural gas emissions are 0, we still have some greenhouse gas emissions associated with the electrical grid. And you can see that from 2030 to 2050, it's this gradual slope as the grid gets greener until in 2050, they're completely eliminated. Looking at some capital costs associated with these conversions, each building conversion is kind of 2 different components. There's the building conversion, which is replacing all of the terminal units. So replacing all those steam radiators with low temp compatible steam hot water generators like Mike was showing in the picture of Carleton College before. It's not just radiators, there's a lot more work that has to go on, new piping throughout the building. So that's what these building conversion costs are. And then there's also the energy plant cost. So this would be kind of that air source heat pump plant that goes on and is built outside. And so looking at the total cost for the town in 2022 dollars, it would be 7.5 million for the capital costs. And we also did a life cycle cost analysis, that's LCCA for short. And a few different, there's a lot of information on this page, but what we want to kind of highlight is the fact that over the 30 years, we plotted out the total cost for not just the capital investments, but for the electric utility. So the projected energy costs for electricity and natural gas, as well as the maintenance. And what we found was that over the 30 years for the town buildings, the total additional costs associated with switching to an electrified system would be around $5.5 million. And this is mostly driven by this orange bar here, which is investment or capital costs. And you can really see the difference here between the size of the orange bar. There's not a lot of capital costs associated with the business as usual case, but by actually investing in these buildings and electrifying them, there's some significant capital costs there. Another thing that we looked at on here is the annual operating cost. So after the 30 years is over, and in 2051, we're just operating the buildings, looking at the utility costs and the maintenance costs for the 2 different systems, we find that the proposed or electrified option is around $25,000 less on an annual basis. And then there's one other graphic to show for this life cycle cost analysis, and it's the kind of the cash flow over 30 years. And down here in the blue dash is the business as usual case, and then in orange it's this electrified option. And we can kind of see a couple of step increases, and these are associated with converting the buildings. And then it kind of levels off again as after those buildings have been converted. It's just an interesting graphic, and it's kind of helpful to see the lift associated with each of those building conversions. And at this point, I'll pass it off to Mike to talk about the school buildings.
Yeah, and as we transition to the Acton-Boxborough Regional School District buildings, it's kind of important to highlight a few differences between the analysis. You know, as an overall approach, the methodology that Ian went through before about creating the business as usual case and calibrating our models, that's all the same. But there's a lot of differences between the buildings within the school district and the town buildings. And the school district buildings, as Kate mentioned, are much larger. They have much different occupancy, different usage, and they also have different HVAC systems installed within them than what we found over the town of Acton buildings. The other key thing to point out is with the school district, we're working with a electrification goal of 2050, not 2030. So that timeline really, it does change things dramatically in terms of when you invest and how much life you're getting out of the existing assets. Just to start off with the high school. The high school building, we did establish the business as usual case for all of the buildings, including the high school. And part of that, we did do the model calibration, looking at the actual metered energy use versus what our model was putting out, and adjusting our model, some of the inputs within our model, to get both the heating and cooling within 1% of the actual metered data. Creating, again, the thermal profiles for all of the school district buildings. Again, here we see the high school business as usual case, in red on top representing the heating load, the average monthly heating load. In blue below the line, we have the average cooling load for the building. The outputs from our business as usual case set up the baseline for us to be able to compare all of our electrified options and scenarios to. The outputs we get are the energy use for the building, broken out by heating and electricity and natural gas. We also have the associated costs with that energy use, again, broken out by electricity and natural gas. And then finally, and I think maybe the most important part for this study, is looking at the associated carbon emissions associated with the heating and cooling systems for these buildings, again, in the metric ton equivalents of CO2, and also broken out by natural gas and electricity. For the high school, for the electrified system that we landed on for the high school, we proposed a hybrid approach. This hybrid system includes multiple different HVAC assets. It's a very large building with a lot of different end uses in there. And so we have first a solar thermal array, which is providing a small amount of annual heat for the building to kind of take care of the year-round heating load. Next, we have optimize an air source heat pump system that can provide the majority of the heating and cooling for the building. And then finally, to supplement the air source heat pump system and provide the peak cooling and peak heating, we have an air-cooled chiller, and we have a electric boiler. And we can see at the very bottom, there's a very small sliver of blue that represents the air-cooled chiller cooling, the annual cooling associated with the air-cooled chiller. And at the top, we see a very small sliver of red associated with the electric boiler. So the equipment that we're buying, that air-cooled chiller and that electric boiler, they may seem like large assets to purchase and maintain, but they're only being used for a small portion of the heating and cooling load. I think in this case, both of them are at or under 5%. And with the electrified option established, we can then compare the output from from those air source heat pumps from our proposed electrification case back against the BAU system. And what we're seeing for the high school is we have a dramatic decrease in energy use. We have an increase in energy cost or utility costs. And then we have a complete reduction or elimination of natural gas, carbon emissions, greenhouse gas emissions by 2050. So for the other buildings, just to touch briefly on the other buildings in the included in the study, we have the R.J. Gray Middle School. The electrified option for the middle school included an air source heat pump system. The air source heat pumps were able to provide 100% of the cooling load for the space and a majority of the heating load. We did require, as you can see in this top graphic here, the small sliver of red representing a remaining heating load, which we have an electric boiler proposed to take care of that peak heating. Again, not used a lot, but it's there for those coldest days, a couple weeks of the winter. For the Parker Damon building, again, the electrified option here is more of a hybrid option where we have air source heat pumps optimized for the majority of the heating and cooling loads. However, we do have that remaining peak cooling condition and peak heating conditions where we need to provide an additional HVAC asset to take care of. And for the cooling, we've suggested an air-cooled chiller. And for the heating load, that peak heating load, we've also proposed an electric boiler. For the admin building, we were able to provide air source heat pumps to cover the entire heating and cooling load. So it's more of a simplified system. We don't have that. We don't have any issue maintaining the entire heating and cooling load with just the air source heat pumps here. So it's a much simplified approach. And again, the administration building is one of the smaller buildings within the school district. For our investment plan for the school district scenario, we have 2050 as our goal for full electrification. And what we've used to inform the different building conversion and electrification dates for these buildings is based on maximizing the useful life of the existing equipment. So we're looking at, say, for the high school, we're looking at how old are the boilers, how old are the gas-fired, how old is the gas-fired equipment within that building, and if it's due to be replaced, in 2030, 2033, that's when we would suggest doing this building conversion. This way, the school district can get they've already invested a lot in the buildings that they have, and we want to try to maximize that investment by not replacing equipment prior to when it's necessary. Looking at the total greenhouse gas emissions reduction for the school district, we can see in this chart here in red the emissions associated with natural gas, and we can see in green the emissions associated with purchased electricity. The blue line across the top represents our business as usual case, sloping downwards slightly because of the eventual greening of the electrical grid. And we can see that if we just did nothing in the business as usual case, we would never really get to any goal of eliminating carbon emissions by 2050. So taking action to do that, we have the first step decrease is the high school in 2033, dropping the natural gas and the electricity. And in 2044, R.J. Gray, reducing the emissions further. And then finally in 2049, Parker Damon and the admin building, eliminating all of the natural gas emissions for these four buildings associated with these four buildings, HVAC systems. And then finally, the remaining electricity emissions are assumed to be eliminated because of the Massachusetts commitment to sourcing 100% renewable energy for the purchased electricity by 2050. So the costs are broken down. Capital cost investments for these electrification options are broken down into two major buckets. One being the building conversion costs, going through and retrofitting all of the end uses of heating equipment within the building, VAV boxes, radiators, reheat coils, things like that. And then the central plant, or I'd say maybe infrastructure cost for the air source heat pumps, for the electric boilers and air-cooled chillers, where we've suggested those as the energy plant costs. And total for the school district is $35 million of investment over 30 years. But however, as Ian was mentioning, we don't necessarily just look at this first cost in 2022 dollars. We look at the life cycle cost for the entire project. And that life cycle cost analysis, it's over 30 years. It's an economic comparison from our electrified option to the business as usual case. We factor in the cost of all of the utilities, electricity, natural gas. We also look at all the operational costs associated with both the BAU and our proposed systems. And we also include those capital costs that we just talked about, that $35 million. But also we look at what would it cost over 30 years to maintain the business as usual case. Because within the business usual case, there's going to be renovations and equipment replacement that's going to have to be accounted for. So we can get an economic comparison that is apples to apples in terms of evaluating the electrified systems versus what we're normally doing in these buildings. When we look at it on a 30-year present value basis, the electrified options are approximately $15 million in cost compared to the BAU. I know there's a lot of information on this chart, but just focusing on the chart to the right, the orange line, the orange bars representing the investment cost. Again, that's the most significant component of this electrified proposal. And you can see that the electrified option for these represents the biggest portion of the biggest capital investment will be for the buying the new equipment and retrofitting the buildings. From an operations perspective, we see that the annual operating costs for the school district, the natural gas costs are eliminated, the electricity costs increase, and the maintenance costs also increase, resulting in a total annual increase in operational costs for the school district. And when we look at the actual the investment over 30 years, we see the major step increases helping. I think this sort of helps to kind of visualize where the school district would need, when and where the school district would need to be prepared to invest or have some sort of capital infusion into the budget to for in 2033. This first step is for the high school conversion, followed by 2044 for RJ Gray, and then finally in 2049 Parker Damon and the admin building. And with that, I think we'd like to hand the presentation back over to Kate and Andrea.
Yeah, so I already see some hands being raised. I'm going to go ahead and promote folks to panelists, just so it can be a little bit more personable. And then we can call on folks. You don't have to accept the invitation. You can stay as an attendee. You'll receive an invitation.
Does it make sense to stop sharing, Andrea?
Yeah, that's a good idea.
Yeah, we can always bring the presentation back up if there's any specific questions on the slide.
So thank you all for attending. That was a huge amount of information. I'm sure that both Andrea and I would like to comment. The difference in greenhouse gas emissions in 2030 and 2050 are substantial, right? So you saw that the town would still have carbon emissions in 2030, and that's because of the grid. The school district final result was at 0, and that's because we were looking at 2050. But the grid emissions, of course, can be altered by a commitment made by the organization to run on clean electricity. And there's been a lot of discussion about that here in town. Andrea, do you want to say more about that?
Yeah, so that slide 17, which we don't have to go back to, but it shows the grid emissions. I guess one thing to keep in mind is the role that Acton Power Choice, the Acton Power Choice Green Program plays in Acton. Since we do purchase our renewable energy from Acton Power Choice, even though we are getting energy from the grid, we're also supporting renewable energy projects in the Northeast. So that's just one little thing to keep in mind when looking at that graph.
And the district it buys renewable energy credits for wind from the Midwest. So there are a variety of ways to try to address emissions in the electricity, and including working on state policy to reduce it for the state as a whole.
That's right. And then I guess one last comment is that that big chunk of orange in both the schools and the town, it shows the importance of getting state and federal funding to really reduce those capital costs. But with that, I did see some hand raised. The only problem with promoting people to panelists is now that the hands aren't popping out. Oh, they're there.
There they
Okay.
go again. Yes, Jim.
So David, do you have some questions for us, for Salas O'Brien?
Yeah, yes, hi. First a comment on the slide. Someplace you use tons and someplace you use MBH, which I think is thousands of BTUs per hour. I would prefer consistent units. You can choose one or the other, but it's hard to compare when some say tons. I mean, I can do the division, but it would be easier if they were consistent in the slides.
Yeah, I think go ahead. Sorry.
No, please go ahead.
I was going to say that usually I think what we've tried to do is for heating equipment we've used MBH, and for cooling equipment we've used tons. I think that's sort of how we've done it, but it's difficult with the air source heat pumps being a piece of equipment that does heating and cooling. So it's it can be a little confusing.
Yes, I understand that, but still, if you're, often the key thing is actually heating here. But anyway, I was wondering if your the sizes that you set on the equipment assumed any energy efficiency improvements in the buildings. I know you said you'd be replacing, radiators with radiant panels maybe, or whatever was appropriate. But are there other energy efficiency improvements in the older buildings?
Yeah, so part of the project was to look at what ECMs, the town or the school district could implement, and we've got I guess a list of those in the full report. But for the analysis of the sizes that are being replaced, we haven't taken any credit for those ECMs.
Oh, okay, thank you. The other thing I wanted to say about the library and the schools is that those buildings are not occupied overnight, right? And so in our area, the difference between the nighttime and the daytime temperatures on average, no matter how cold it gets, is about almost 20 degrees here. So even if we're talking about a minus 12 degree day, a night, during the day, it's going to be above zero. What that means is in some of the places where you've added electric boilers, they may not be necessary, right? If the temperature of the buildings drops 5 degrees overnight, no one cares, no one's there. And so, and at a minimum, I understand that you may think that there needs to be backup, and I respect that, but at a minimum, those systems should not be automatic. They should be able to be shut off so they don't kick in when we don't want them to and consume extra electricity, or the parameters of when they kick in should be highly customizable, because those things consume extra electricity. If they do it on a normal night, all the month of January when no one's in the building, that doesn't make any sense.
Right. Yeah. Agreed.
And I was looking at your financial analysis, and I was wondering, does I think the last line in them, I don't need to call it up, but below maintenance, you had investment or something in on those slides. Does that include in the business as usual column, the replacement of units, of like kind if we didn't take any action? Is that what that is for?
Yeah, for the business usual investment costs, we're looking at just a simple like one-to-one replacement for if you have a boiler, we replace the boiler. We didn't look at trying to renovate those buildings. It would have been pretty difficult to try to get an assumption that when you renovate the town hall in 20 years, you're going to maybe improve the efficiency of the systems or change the systems. It'd be kind of too difficult to predict that. So we just went with a like for like replacement based on ASHRAE recommendations of what is the expected service life of any given piece of equipment.
Great, thank you. That's all for me.
Thank Thank you, David. And then I think we have Kim Castens.
Thank you. You mentioned replacing equipment, but you didn't say anything about improving insulation or sealing leaks. And I wondered if that's part of the plan, and in particular, if it's possible to push it to the point where you could skip the extreme days air-cooled chiller and electric boiler. So that my first question is, what's the plan for insulation and sealing leaks?
Yeah, so I think in the back to I think what David was asking, sort of with the energy conservation measures.
Okay.
I think
is
in
that
some
what ECM is?
yeah, sorry, yeah.
ECM.
So the energy
Okay.
conservation measures, we did get a list of some of those together. A lot of ours were more focused on, I think, like MEP systems, focused on like
What's
energy.
MEP?
Sorry, mechanical, electrical, and plumbing systems.
Uh-huh.
Focused mostly on that, but there were some buildings, I think RJ Gray might be an example, where it's perceived to be very leaky or a lot of infiltration in there. And so that area we looked at, I think one of our recommendations was air sealing, maybe instead of insulating the entire building. But if there was ever a roof replacement, there might be an opportunity for upgrades to the roof insulation. But right, all these things could help reduce the overall size of the potentially the installed size of the systems, but also maybe more important to the reduction of the natural gas, the carbon emissions would be just how often they're used. So even if you still install the same size, like you might not be able to get a reduction in the peak heating load on the coldest day of the year, but you might be able to say we're not going to run this boiler that often, or this air source heat pump as often, with an improved envelope performance.
Okay, just since you have such a few number of days for these pieces of equipment, if there's a way to, sort of work the conservation and insulation and energy conservation measures, so you didn't have to put those in, that seems like a savings. And then my other question was on the first business as usual graph that you showed, I think it was for the public safety facility, there was a cooling load in December, January, and February, and I wonder why on earth they don't just open the windows?
I believe that's there's a data center in the public safety facility, and that uses cooling year round.
Okay, thank you.
Just saying these are fabulous questions, you all.
Yeah.
We are blessed with a lot of engaged folks.
Jim.
Hi. Well, I guess I was looking for some qualitative reaction from the Salas O'Brien folks about a few factors and whether they would make any material difference in this analysis. The first was anticipated temperature changes over the next few decades. Seems like we're going to probably have more cooling load and less heating load, but I don't know if that would be enough to change the analysis in any significant way. The other factor I was wondering about was relative changes in utility prices between like electricity and gas, because it seems like, if we're headed for success with climate, we're probably going to need to make fossil fuels more expensive and electricity less expensive. And the last factor I was wondering about was the discount rate. So it looked like the life cycle analysis was sort of a straight line analysis without, thinking that the cost of money is that there's a cost of money. So I wonder about any of those things and how they would impact the overall results of the study.
So I can answer this one, Jim. So your first one was about the
Temperatures.
So the temperatures, yes. So I think we did not use any temperature escalation and global climate change kind of factor in our analysis, just because it's highly variable, and introducing another variable into this analysis just kind of makes the results even a little bit more uncertain. So that is something that we didn't include. However, I think, to your point, in 30 years, if the global temperature and the temperature in Acton is, 1.5 degrees warmer, that would affect the the sizes of the systems for sure, and the annual energy, and definitely shifting more towards cooling in terms of annual energy, not necessarily in terms of peak heating and peak cooling. Those extreme peaks are likely still going to occur, so that the initial system sizes will still likely be similar, but the annual energy consumption will shift more towards cooling. The next was about utility escalation rates, and so we did include electric escalation and natural gas escalation, and for that we used the Department of Energy publishes a energy escalation rate calculator, which you can find online. And it uses the last 20 years and extrapolates based off of the last 20 years of energy rates moving forward. We did include inflation in all of our capital costs as well.
Oh, okay.
So that is all included. And we also worked with the town and regarding discount rates, both the town and the school district, to kind of confirm that. I think it was around 4.5%. Is what we ended up using in our life cycle cost analysis. Was that all your items?
Yeah, that's great. Thank you so much.
Yep.
And I do see a hand raised by Brian. So Brian, I'm going to go ahead and I'm going to put allowed to talk.
Thanks, Andrea. Can you hear me?
Yes.
Oh, good. Yeah, hi, Brian Aldrich, 56 Mohawk Drive in Acton. Yeah, ground source heat pumps. So I first heard about these 15 years ago, at which time they were too expensive for homeowners. And so and more for town municipal buildings, which I see we're doing. I would just, I did air source heat pumps 2 years ago with Mass Save, and we love them, and my home here in Acton. I was just curious, are ground source heat pumps still too expensive for homeowners? And of course, I'm thinking of the McMansions that are going up all over the suburbs of Boston, and these people can afford these $1 million homes and $50,000 more for ground source heat pumps. Maybe they should be forced to do that. Although I know we've got to go by carrot, not stick. But I mean, really, they build these huge square foot things that increase the carbon footprint. And there's probably 4 people living in there. I mean, I'm talking like a fanatic, I know. But anyway, are ground source heat pumps going to be anywhere within striking distance for wealthier homeowners in the next 10 years?
So just to kind of briefly just touch on how we looked at ground source heat pumps for these electrified systems here. We did look at those as an option. We did find that the cost, the air source heat pumps provided a better economic performance for the 7 buildings that we looked at. And so we did look at, especially at the high school, and we looked at the school district as an overall campus. Putting in a ground source system there, and the economics just didn't pan out against versus air source heat pump systems and individual building systems. Where we're seeing ground source be from our experience and what we're working on from Salas O'Brien is we're seeing ground source be a competitive alternative when we have a already established campus setting where we already have buildings connected together that can share and utilize the heating, the simultaneous heating and cooling that can be available from like a ground source system, and that helps foster that helps make the economic case better for ground source systems. And we're talking much larger scale, something on the order of I'm just trying to think of what we're doing at Smith College right now, but it's in the order of a couple thousand tons versus some of the individual buildings we were looking at here were in the hundreds of tons sort of range.
May I jump in for a minute? I just want to mention, Brian, that the 2 new buildings are both geothermal, the fire station and the Douglas Gates Boardwalk Campus School building. And so for new construction, especially public buildings where we're going to be owner operators for 50 years, it makes a lot of sense to go with geothermal for in those situations. It appears. I mean, you got to do the math, but and in addition, I want to let you know that there are vendors working on residential models for geothermal that are including financing. And that is what allows homeowners to consider investing in a way that might work, even though they're not going to own or occupy for 50 years. Excuse me. And I know that, for instance, Dandelion Geothermal is one of those vendors that has come up with a model that includes financing. So they're beginning to do business in this area. There may be other vendors as well. So that's a thing to consider for folks.
Thank you. That's very helpful to know. So I guess it's safe to assume in 14 years, obviously the air source heat pumps just really accelerated in the technology, efficiency and cost. And so that makes sense. Yeah, I first heard about ground source heat pumps. I was with Cornell Cooperative Extension out in Central New York, and there was a presenter there in 2008. I was only dimly aware of the technology before, but it sounds like, yeah, larger investment. When you're building new construction, all those things are more cost effective as opposed to retrofitting. And so that's all. Thank you all for your work. It was very encouraging on all fronts.
Thank you.
I see Ann Chang, and you have your hand up.
Yes, I'd like to know several things. How confident are you in the states being meeting the 2050 deadline for their electrification? Judging from what the legislature has done recently and how they put things off, I'm not at all confident that it'll be by 2050. My second question is, I'd like to know how long air source heat pumps last. How frequently do they have to be replaced? But my major questions will be about the library when you get to that, but these are just general questions.
Yeah, in terms of the state, it's difficult to predict that, what they're going to do. But what we can really count on right now, the only thing that we can really count on is what they said they're going to do. We know it can change, but that's what they've put in writing so far. So I think that's our current marching orders. But we can always take that with a little bit of a grain of salt, knowing that the state maybe hasn't always fulfilled all the commitments that they've put out there, or that they've delayed them.
So I'm going to pop in on that and just say the commitment to clean up the grid, Anne, is proceeding apace. I think it's reasonable to expect that electricity emissions are going to be down to zero by 2050, certainly, and hopefully sooner. So the commitment for the state is, I think it's Andre, it's net zero greenhouse gas emissions by 2050. So that remains to be seen. That's a bigger stretch, but I think it's reasonable to expect that our grid is going to be clean. Certainly by 2050. I mean, the economics are all pointing in that direction. That's my guess. Mike, and there were other questions Ann asked as well.
Yeah, for the air source heat pumps, I think the ASHRAE service life, expected service life for the air source heat pump is 15 years. And so that's just their recommendation. So you're probably, there might be some that fail before 15 years. But if you provide, annual, regular maintenance on the systems, you can expect that it's possible to get more than 15 years out of it.
Do you have to have special people in town to do the maintenance rather than the people that we already have?
So I think that any refrigeration repair person that could repair your air conditioner could also do the same work on an air source heat pump system.
So perhaps that you should include in your cost estimates the cost of contracts to cover these kinds of breakdowns or costs for things, because what you're saying is the people that we now have on staff can't do it.
Yeah, it's possible. I think that the folks that are right now maintaining if you have a refrigerant-based air conditioner, which I think most of them are, that those could be the air source heat pump systems that we're suggesting here could be maintained sufficiently by any refrigeration repair person.
And there are high level maintenance costs built into this study. They didn't get down into the nitty gritty 1,000-foot level, but the district, for instance, has a HVAC technician on staff full time. So we're certainly set, and the town as well already carries equipment like this where there is air conditioning, and services it. So it's not a moonshot by any means.
I do think that how that translates to the residential market is, I think, worth just bringing up, and I'm glad you brought it up, Ann, because there are, we're talking about the school district and the town that have dedicated people to provide maintenance, whereas we all know that in our houses we don't really have that. So knowing that the air source heat pumps can be maintained by probably the same refrigeration technicians that come out to to service your system right now is, I think, is key.
Okay.
Did you have one more question, Ann?
No, my major questions will be when you get to the library part, because that's the building I'm interested in.
Yeah, I think if you want to go ahead and ask now, I think that's appropriate. I don't know that we have a specified library time.
All right, I'd like to know how many heat pumps you're going to need for the library. What was the other? One of my questions has to do with our Acton's power choice. If we didn't go to the top power choice or the most expensive power choice, I would like to know, say we went to the middle or I think there are 4, instead of number 1, or use number 2 or number 3, would we save money? And the other thing is, how much of the library will you have to, tear apart to do these conversions?
I think we can probably talk to the heat pump quantity and the building conversion scope within the library, and I think maybe Andre, you could jump in on the power choice impact.
Yes, sorry, the power choice impact economically, or what was the question about power choice?
Yeah, if we were right now, I think we're using some sort of number 1 basis or the top level, and if we use 2, 3, or 4, if there's other tiers of that program, would we save money?
Is that what you were asking, Ann?
Yes, that's what I'm asking. We're using the most expensive. I was wondering if we, mainly because of the costs, the inflation cost right now and the pressure on the town's budget, if we went to a lower electricity cost per unit, which is not as clean, but is lower, we would, I don't know how much money we would save, but I was wondering whether it would be effective. We just wouldn't reach our goals quite as fast.
Yeah, so we would certainly save money by going to a lower cost option. But like you said, it sort of is, being at the Acton Power Choice Green aligns with the goals of the Climate Emergency Declaration and the Climate Action Plan. So it's definitely an interesting conversation to continue having as prices continue to increase. But for the moment, we are on Acton Power Choice Green, and certainly going down to a lower level would lower the cost, but emissions would increase.
Right, but it might. Well, I want to make sure that we have enough money to run the town, I guess.
And if it's helpful, there's a general expectation among people who work in energy, meaning people far more expert than myself, that electricity prices are going to settle down in a year or 2. So that they're not going to continue to be, we're living in a time of elevated prices, but that is not expected to continue.
It is true that when we went out to bid for the new Acton Power Choice program, one of the recommendations was, from the consultants we work with closely, is to stick to a shorter time period to kind of ride out the wave that we're facing right now. So that's sort of the assumption, that prices will stabilize and that we're in an unusual peak.
And Mike, do you want to speak to Ann's other questions?
Yeah, for the air source heat pumps that we've part of our electrified option, we've included 2 commercial size air source heat pumps that will be located outdoors or potentially on the roof. at 75 tons each, or I think that translates to 900 MBH capacity. So those are the two large air source heat pumps that we would need to maintain as part of that project, or part of that electrification. Both of those pieces of equipment are going to generate hot water to heat the building in the winter and chilled water to air condition the building in the summer. In terms of the building renovation scope or building conversion scope, the cost for building conversion that we included involved going through and really touching every piece of heating equipment within the space. So if there was there are some built-in radiators along the perimeter, those would have to be replaced with radiators that would be sized to operate at a lower temperature hot water. I believe there's some reheat coils throughout the space. Those would also have to be replaced to operate on the same low temperature. Right now, they're I believe 180 degrees is the temperature that the building operates at, and so we would suggest going down to something as low as 130 degrees Fahrenheit. And with that, we just lose a lot of the heating capacity. The equipment that's already installed is very much derated at a lower temperature, so we have to replace those coils with larger coils, replace those radiators with larger radiators. And so we would envision going through and doing a building conversion scope that would need to replace every piece of heating equipment within the building.
Well, I'm really not sure where the heating equipment is at all. How when you say you need two commercial sized heat pumps outside, how large are those?
Off the top of my head, I don't have the sizes, but they're probably comparable to the size of one of the large rooftop units. I don't know, Ian or Jake,
So
if we got access
is it 10 feet by 5 feet? Is it 3 feet by 10 feet? I mean, are we going to have to get the Historic District Commission to say, okay, we can put this out, where it can be seen? No, those are the kinds of.
Yeah,
I mean,
that would
definitely.
I think that would definitely be a consideration, especially for this building and for the town hall. And I think we might be able to quickly here. We might be able to find the sizes of this equipment, and if we can't find it within this call, we can send it over to Kate and Andrea to forward to you.
Okay.
And it looks like, Jim, did you raise your hand again afterwards? Maybe that hand is raised from before. And same with Brian, I'm assuming. Great.
No, that was an accidental raise. So I'll bring it back down.
Okay. David.
Yeah, I just wanted to make a comment to Ann's concern. So one of the things is that all the existing air conditioning equipment that's outside goes away in this conversion. So although the heat pumps may be slightly larger, they replace the air conditioning units and really don't take up much more space than the air conditioning units. I mean, a little bit maybe. It depends on some of the details, but it's a trade.
Yeah, for example, over at the town hall, there's an equipment yard that has like an air-cooled chiller, I believe, installed in it, maybe a generator as well out there. So we would be taking that out and replacing that with the air-cooled equipment within that existing enclosure, or potentially expanding that enclosure to depending on the clearances and the final equipment sizes. So what we're looking to do is kind of really just stick with what's already there in terms of the impact to the building exterior and the facade, and keeping in mind that it is a historic building and an important building, for the town.
And I just found some rough sizes for the air source heat pumps that we were looking at for this building, and they're pretty similarly sized to the units that are already on the roof, and be a bit longer. It looks like they're about 7 feet tall by 4 feet wide by 20 feet long. There'd be 2 of those.
Well, since the
Thanks,
current air conditioners leak and go into the roof, I think I would like something that doesn't leak. But that is huge, isn't it? So you're saying you'll put them on the roof and not on the side of the building, which
yeah, I think both are options, and I think that's really a design sort of detail. You know, we have the overall kind of picture, but yeah, would this roof support it? Not sure. There's a flat roof on the back. Could that be utilized? Not sure. There's also a parking lot and some, you know, a decent amount of land nearby, which could also be utilized, but that would just be part of the design process by whatever design team gets involved in the project going forward.
So
Well, the roof has got the gable type things on it, so the HVAC system can't be seen by the street, which was a requirement from the Historic District Commission when we built the building. So that's, yeah.
That's good.
Thank you all, and thank you all for the active engagement at the end of this presentation. I think it was really helpful to hear your questions. And thank you to Salas O'Brien for being here to answer them as well. You know, this assessment is one of many assessments because this is, you know, a first initial piece of getting us, you know, giving us a sense of what we have to look into for a lot of these buildings. But more detailed design would be needed once we were to move forward with electrifying these buildings. So this is like a broad view, which is really important in terms of helping us figure out how to prioritize future capital expenditures and plan for electrification for these buildings. So it was a really important critical step, but there's definitely more work needed for the more specifics for each building. But this is a really good start. Kate, I don't know if you want to say any last words before we close out.
We're grateful to Salas O'Brien. They've done a terrific job with this study and the report, and also with continuing to be available for engagements like this. So thank you. And yes, both organizations need to take this 30,000 foot look and decide how to move forward. And any movement forward will require more in-depth engineering and design work, as Andreas said. So we're delighted to have had the funding to do this study, and it gives us a really good basis for considering what we do next. So many thanks to all, and especially to the engaged citizens of Acton.
Yeah, thank you all. Appreciate it.
Thank you all so much.